Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to start to talk about the electrostatic energy as well as the capacitor. So in here we'll start to discuss where does the energy is stored in a electrical system. Maybe it could be in the form of the electric field itself. So we'll try to do some thought experiments to develop the idea that you could store energy in the form of the electric field. But before we get started, please consider subscribing as well as liking the video, and also please check the description below for the notes in this entire discussion. So let's start with the electrostatic energy itself. So let me remind you that if I have two particles from far away, I'll call that U or the V to be infinity. No, sorry, it should be 0. But if you bring it close enough, we will define this. We will define the voltage of the system will become KQ over R. This is what we did on the last discussion. So what about if I start to bring out another particle from far away and bring it close? Well, now first of all, this guy here would mean that we'll have the potential energy to be KQ1, Q2 over R12. So if I introduce another particle here, we will so so we will know so the only thing that we'll know is the change in the voltage itself. We couldn't really determine its voltage because in fact that in here is that we already have a initial voltage. So we will need to think a little bit much more further than that. So this change of voltage of the second particle here will be the distance from particle 1 to particle 3 and then particle 2 to particle 3. So we'll have the KQ2 over R2 plus the KQ3 over R3. No, sorry. It's KQ1, R1. 1 to 3 and 2 to 3. So therefore, I could write this change to be KQ2 over Q23, no, Q3 over R23 plus KQ1 Q3 over R13. So this is pretty much the potential energy that you get just by only multiplying it by the cube. And so you could determine the original potential energy. It's pretty much the change in the potential energy is U minus the KQ1 Q2 R12, this one. So you could just rearrange it to get this KQ1 Q2 over R12. So this gives a very useful formula. You would get that the sum when I is not equal to j until n, it will of kq I qj over rij. So pretty much ij means, so rij means that what is the distance between particle I and particle j, and qi and qj means the charge at I as well as the charge at j, and the k here is just constant. So this gives a very useful formula just to actually formulate the potential energy of a entire system. And so now we could start to discuss about the capacitors itself. So pretty much what capacitors is that it basically stores energy in the form of the electric field. In the form of electric field. And And the way that you create a capacitor is by taking two conductors. Let's say the conductors are cylinder, and they each have the same charge. So that's Q, and then this guy is negative Q, let's say. So pretty much this whole capacitor should be neutral. But each of the conductors have the same magnitude but different signs of charge. One of them is positive, the other one is negative. But instead of actually discussing these kinds of capacitors, we'll just discuss a very simple model of the capacitor, which will be the plate capacitors. So in here I will have a plate in which it has an area of A, and it has a charge Q as well as negative Q. So last time we have already figured out that the electric field for this plate has to be sigma over 2 epsilon 0. And by the way, last time when I discussed about this, I somehow got a sigma over epsilon 0, which is not the correct case, but it could be used when you're dealing with the surface of charge. But for plates, it should be sigma over 2 epsilon 0 for its electric field. So we can now determine what the electric field is, which is pretty much only, so it's the total electric field. And so if you actually try to take a look at this diagram here, we would have a positive as well as a negative charge. The positive is the source of our electric field, and it will gonna point towards the negative charge. So we can draw something like this. So we would know that this electric field should be sigma over epsilon 0, because it's pretty much the summation of this from the positive side as well as this from the negative side. And you know that the electric field should be constant. But don't forget about this. This assumption we made was based on a infinite plate. But in here we are dealing with a finite plate, which means that if you actually take a very small scale observation, probably near the center, the result should be very similar to the one that I will be discussing here. But in actual data, the ones on the corner or the edges will have different values, but if you take this as a whole, it is a very good approximation of the experimental data. So we'll just use this. So we have obtained this electric field here to be sigma over epsilon 0. So we can now determine what's the work. The work is pretty much the integral of the electric field with the dr vector. And let's just take the dr vector goes from here to here. So this will be the lower one, and this will be the higher potential. This is higher potential. I'll say V positive, and this will be V negative. So, oh wait, so this means that this should be the work. No, sorry, the voltage. So, computing this voltage itself. So, wait, it should be in the negative of the integral E vector, dr vector, yeah. So we can compute what this voltage is. It's the negative of the E vector. The E vector itself is sigma over epsilon 0. And the sigma is pretty much Q over A. So we could write Q over A epsilon 0. Integrate that with the R vector. And why can I actually bring this value out? Well, it's pretty much because that the value itself doesn't fully depend on the electric field. It is as if the electric field is always constant, no matter if you move your measurement points. And so anyways, something that you would also need to look at is that this R vector as well as the E vector is pointing at different directions. So this means that the dot product inside here would be negative. So this should be a positive sign. So remember about this. The electric field, which we compute by using Gauss's law, doesn't define its direction. You need to know where its direction through the definition of charged conductors, in which its electric field should be pointing perpendicular to the surface. And so that's where our logic could state that it's pretty much in different directions, which means that we need to multiply this by a negative. So we'll get this. And so now what's the integral of this dr technically? This dr here goes from a value to another value, or pretty much if you do it in terms of the distance, you would know that this would be d, which is the difference between the placement of our charge plates. So we would have qd over a epsilon 0, and this is v. So this gives a very good observation, is that the higher the charge that you put into your plates, the higher the voltages. And so we can now start to talk about a very useful concept when you deal with electrical engineering, is the capacitance. So C here is defined to be the Q over V, and this is pretty much in general. And for charged plates, you could actually observe that the C here is pretty much A epsilon 0 over D. And anyways, don't forget that this is inside a vacuum. When you have this surface here to be inside vacuum, because if you introduce a material into it, you would know that you would also need to consider the electric field caused by the dielectric itself. So observing this, we know that the capacitance unit should be coulombs per volt. Well, this coulombs per volt is pretty much useful when you are trying to do unit analysis, but it is much more convenient for electrical engineers to observe this as something which we call as the farad. So this is pretty much a unit of capacitance. So it's pretty much how much charge that you could contain over a certain change in voltage. It's pretty much that type of meaning. So with this, we can start to develop the idea of the energy inside of this voltage difference in a capacitor. So the U here should be the sum, the work should be the sum of the change of works. So this change of work will be the integral of Q dV. So this is something that we have already obtained last time, in which we know that the dW equals to the Q dV. So you just put this inside the integral, and what you observe is that what you know is that Q is pretty much CV. So it's pretty much this type of integral, and normally when you deal with electrical engineering, the C here is a constant. You would never use a very different capacitance in terms of the voltage. So instead, normally we will always deal with a constant capacitance. So we can just bring it out and then do the integral, which we will get half CV squared. And you would just compute this within the change of voltage, V final and V initial, let's say. And it is pretty useful if you state that if the voltage is 0, there's no work done. No, sorry. Is that, no wait, yeah. So this is pretty much the potential energy. So we'll just define the potential energy when it is at zero, when the voltage is zero. So we could just obtain this half CV squared, where the V here is the final, or it's pretty much the definition of our potential energy. So what we observe here is that it has a very similar relationship with the spring. It's half kx squared. So you could think of a capacitor as like a spring. So if I have a capacitor here, and I haven't really discussed about current yet, so I'll just try to discuss it in a much more easier way. So let's just state that we are putting putting electrons into one of the plates. This would mean that there should be electrons going out, because we are trying to preserve this guy's entire charge. And so after this deposition of electrons, you would have a collection of electrons here, as well as a collection of protons there, or holes pretty much. And when you actually try to add much more electrons into it, you would see that there is some form of repulsion going on inside of one half of the capacitor. So this is pretty much very similar to a spring. So you could just imagine that it's like a box here, and then you are trying to push a spring into this wall, I guess. So the much more electrons, or the much more charge inside of this half of this capacitor, means that you are pushing way harder. So that's the intuition in base of a spring, and then it can release its energy just by releasing the spring. So it's pretty much this kind of analogy. So we have already discussed pretty much the theory of capacitors. So let's try to discuss this in a much more electrical engineering perspective. So maybe sometimes it is hard to create a vacuum inside of a capacitor. So instead, to control its capacitance, material engineers use something called a dielectric material, just to make sure that the capacitance is constant. So for practical capacitors, your capacitance will be kappa times epsilon 0 A over D. So this kappa here is something which you call as the dielectric constant. And so now, just like as I did at chapter 1, in which I discuss about dielectrics being able to create some form of dipole, in here we are trying to use that knowledge. So I have this material, and then I have an electric field caused by the capacitor. This dielectric will have its negative charge propelled in this direction, and the positive in the other direction. So in here it's all negative, and then in here it's all positive, right? So this buildup of the dielectric, of the dipoles inside of this dielectric, will also cause some electric field going up, which sometimes you would call that as the polarization. So now, instead of your electric field to be this guy, instead it's just the electric field minus the polarization. So there is a higher capacitance when it comes to dealing with actual capacitors. It's it is having this dielectric constant here. And pretty much you could actually get the dielectric constant just by observing it in a lab. So what we'll gain is that the capacitor, no, sorry. So the capacitance is pretty much the kappa, multiply that by the original computation of the capacitor in a vacuum. Another thing to consider in actual capacitors is the working voltage. And this working voltage is pretty much very similar when it comes to Thunderbolt. So last time we have already discussed about if you have a let's just use Greek. So if you have this buildup of energy, or pretty much the negative Q at the top, and then in here it's pretty much actually positive Q because it's technically a capacitor, but who cares much about the small details. But if there is a very big voltage drop in between these two surfaces, what you get is that the air will somehow turn into a conductor, as it can now create a chain for electrons to channel through, and this is what causes thunderbolts pretty much. So this is also applied when you deal with capacitors. Is that if you apply a very high voltage, when the voltage goes to if it goes above this maximum voltage, what you would have is a breakdown, or the dielectric breakdown. And this is the main reason why you cannot really charge a capacitor much more than this maximum voltage. Otherwise there will be interactions between these charges, and it might sometimes cause even a explosion within the capacitor itself. So it is something important for you to also to remember when you're dealing with capacitors. So maybe you might be thinking, how do we actually increase its working voltage or even increase its capacitance? Well, with that, we could actually do connections between parallel or series. So we haven't fully discussed about a series or a parallel connection. Maybe we have already discussed that during Hooke's law, but in here we will just do a parallel first. So this is a parallel circuit in which this is a series. So let's just do a parallel circuit. So in here I have capacitance 1 and capacitance 2, and I apply voltage as well as a ground. So what we know is that the voltage difference in here has to be V. So from here, there is one thing in which we could actually see straight away. So yeah, anyways, that this guy is one group that's 0, and this is the other group with V. So what you observe straight away from here is that you'd have this working voltage not really changed due to a parallel connection. But something interesting happens when you're dealing with parallel capacitance. So if we try to simplify this into just this one capacitor, so first of all, its voltage drop is the same. And so there is a buildup of positive Q and also negative Q. So is it true? Yeah. So our total capacitance here has to be this Q over this voltage. It's pretty much the same, the QT anyways. And this, and also from this observation, we do see that this C1 is pretty much Q1 over V, and C2 is Q2 over V. And when you're when you're dealing with capacitors, there is also another thing for you to also remember, is the conservation of charge. So maybe like the entire system has pretty much that charge of 0, but if you try to separate it between the one on the positive terminal as well as the negative terminal, the charges should add up. So in here we have Q1 and Q2, right? So that means one thing. This Q total here should be Q1 plus Q2. It's pretty much the charge from here as well as the charge from here. And this should form our Q over there. So we would get this relation. And now we could actually substitute them in to obtain capacitance 1 plus capacitance 2. So this is the relation when you're dealing with a parallel capacitor, is that you could actually increase the capacitance just by adding much more capacitors to each other. But this does not increase its working voltage. So how do you increase the working voltage? Well, to do that, we'll just do that when you're dealing with a series. So you would have a capacitor as well as a capacitor, something like that. So remember, in here it's 5 volts, this is 0, and in here we'll call that as a V, but we don't really care. So what you would observe is that the difference here is V1 and the difference here is V2. No, sorry, why did I put 5 volts there? So another thing to observe is the charge itself. If I have built up positive Q here, this means that there should be negative Q in here. And with this negative Q, I should have positive Q, because this entire component has to conserve its charge. So negative Q and Q, sum them up, you get 0. And so in here, it should also be negative Q, because it's a capacitor. So this is capacitance 1 and capacitance 2. So with this, we want to convert this into pretty much the same idea. We would have this total capacitance and a voltage drop V. And that's V, and that's 0. So voltage itself, remember, voltage is pretty much a state variable. So you would know that from here to here it changes by V2, but from here to here it's V1. But from here to here it should always be 5 volts, or pretty much the V itself. So it's V1 plus V2. And now, remember what V is. The V is, so it's Q over V is C. That means that C is Q over C. So there's a positive buildup of Q, remember? And this positive buildup is literally formed by actually observing this positive and this negative Q here. So what you would see is that this V here is pretty much just Q over C total. And this V1 plus V2 is Q over C1 plus Q over C2. That means you would get the relation that 1 over C total is 1 over C1 plus 1 over C2. Now, when you're dealing with more than 2, but they're all in parallel or all in series, you could always use the formula for the parallel. It's pretty much the sum of the CI. But for series, it's pretty much the sum of the 1 over CI. 1 over CS is the sum of 1 over CIs. And so you would see that sometimes that you could actually increase its capacitance, but not that much. But what it does increase is its working voltage. You do see that if you do see that if I have a working voltage of, I don't know, let's say 5 volts and then another 5 volts, but now it is separated between these two capacitors, meaning that our equivalent capacitance has a working voltage of about 10 volts. So this could be useful when you have limited resources and you really require a high working voltage. So this is the way for you to actually to increase this working voltage. Now, we have already discussed a lot about the electrical engineering itself, but we haven't fully asked the question, the energy and where it is stored. In this case, it's the electric field. So let's actually do this kind of idea. Let's first state the energy density called UE, small UE, is pretty much the potential energy divided that by the volume. And let's do that for the parallel plate capacitor. So, oh wait, volume cube? No, it's just volume. This is volume. There you go. So, the U itself, we have already figured that out. It's half CV squared. And for the volume, if we actually compute it, it should be A times D. And why is that? So in here and in here, remember that this distance here is D and it has an area of A. And we want to compute the energy inside of this entire plate. No, sorry, the space between the plates. So we will just use A times D. That's pretty much the volume. So with this, you do also remember that the capacitor, the capacitance of a parallel plate is A epsilon 0 over D. So we would obtain this to be half epsilon 0 with V over D squared. Now, here's something interesting. What's V over D? Well, last time we have written V equals to the negative, no, sorry, it's the wrong way around. The negative derivative of V is pretty much the E, right? And so if you have this constant electric field, it means that the voltage will be negative V times D. Is it? No, sorry. It's E times D is the negative voltage. So computing this straight away, you would get the E to be negative V over D. Therefore, we would obtain half epsilon 0 E squared, the magnitude anyways, or you could just write it as the E vector squared. So, here's something interesting about this. This energy density doesn't only work for a parallel plate, but it turns out that it is generalized throughout all different kinds of electric fields, not only including capacitors. You could have, for example, two different charges, and you would observe its electric field. This electric field can be computed into its energy density just by using this formula, half epsilon 0 E vector squared, or pretty much the magnitude squared. So, now, when you're dealing with the energy now, you would see a very interesting relation. It's half epsilon 0 with the integral of the E vector squared, or magnitude technically, dr. Oh, wait, what? No, it's dV, with the change of the volume. So this is pretty much a triple integral, pretty much a volumic integral, but but you're dealing with a scalar. So it's pretty much some multivariable calculus that you need to do, but it's much more simpler. Compare that if you actually try to compute a line integral first. So this is a very useful information for us to determine the potential energy at a given electronic system. So that's pretty much all for today's discussion. So please consider subscribing as well as liking the video, and also share this to your friends who really need to understand physics in a much more clearer understanding. So thank you very much, and I will see you on the next video.